Okay, welcome here to Chapter Three's recorded lecture. So, as I mentioned in class, we'll be recording here the last little part of Chapter 3 that we stopped at. So, for both sections there, we stopped at the same point when we were discussing Chapter 3 in discussion. So, it's about 3.7 on here in Chapter 3. And we're going to kind of continue and finish up the chapter here. And again, that means everybody will be hopefully be on the same page in terms of the chapter. Now, we're going to talk about changes of state. And when we talk about changes of state, it does involve those things that we've been discussing, which is obviously state of substances could be solid, it could be liquid, it can be gas. And when we talk about changes of state, is when we go from, say, solid to liquid or liquid back to solid, liquid to gas, gas back to liquid, solid skipping the liquid there directly to gas. And lastly, that sixth transition there going from gas skipping liquid back to solid. Now, we talked about some of these sort of processes earlier on, and we're going to talk a little bit more detail about it. And we're really going to talk a lot about as well the sort of the energy that's associated with doing those processes. So we're going to talk about that energy involved as we do those processes, as we go from, say, solid to liquid to gas, or gas to liquid to solid. Are we putting energy in? Are we taking energy out to do that? And, sort of what happens, if we want to do maybe a little bit of a calculation to try to figure out how much energy is involved or not. Now, there's one topic that we talked about at the very beginning of this chapter that I said we would not, or you would not be responsible for, which is specific heat. And that is still the case. You're not going to be responsible for specific heat in this chapter. But since this is a recorded lecture and we're not sort of time constrained there during lecture, I'm actually going to talk about specific heat here in this video. Just to give you an idea of what it is. Also, I think it will help towards the end here of this lecture when it does mention some stuff about specific heat and sort of how it ties in. In addition, if you're reading chapter 3, maybe it talks a little bit about specific heat in some other areas. So you'll have hopefully a better understanding of what's going on. But I'm going to still stick by what I said at the beginning, which is for an exam or quiz, you will not be technically responsible for the specific heat part of this lecture. The rest of it, obviously, that's not involving specific heat, you are responsible for. But we won't do any type of specific heat calculations or anything like that. But again, I think it does sort of tie in here. And I think it would be good, since it is sort of a recorded lecture, to sort of cover it. So again, you have a better understanding of sort of what's going on. It'll hopefully, like I said, help you understand maybe some of the other concepts that we are going to be talking about and you are responsible for. So what we'll do here up front is just kind of jump a little bit into specific heat and sort of what it is and, some things about it. So first off, specific heat, and if I spell it right there, specific heat. And specific heat is basically the energy that is required to raise 1 gram of a substance by 1 degree Celsius. It's kind of a very similar definition to actually what a calorie is, which I think we saw earlier on in the chapter. Calorie is the energy required to raise 1 gram of water by 1 degree Celsius. When we talk about specific heat, we oftentimes will talk about the specific heat capacity of a substance. And when we talk about specific heat capacity, it has usually units of joules per gram per degree Celsius, or calories per gram per degree Celsius. And a reminder that joules and calories in terms of units are very common units of energy. So again, some of those common units, as we've talked about, joules are calories. And the relationship between those two is 1 calorie is 4.184 joules. So again, that's a way you could convert, between these two very common units of energy. Also, a reminder that that C here is actually a lowercase c, and it actually does make a difference because there is a capital C, and I'll exaggerate the C there. Capital C here. One capital C, which is usually more a nutritional type calorie, when we're talking about food and that type of stuff, actually equals 1,000 of the little calories, little c, and that's actually equal to 1 kilocalorie, which is 1,000 of the little calories. And sometimes on gym equipment and stuff like that, you see how many calories you burn, capital C, but a lot of times they used to just put up how many kilocalories you're burning, even like on the treadmill and stuff like that. So those are two very sort of common units of energy, specifically the calories with the lowercase c, and joules, very, very common way to express sort of energy. Uh, Kilocalories, also very common, and kilojoules, also a very common unit of energy. Remember that kilo is basically 1,000, sort of conversion of that. There's 1,000 joules in a kilojoule. And obviously 1,000 calories, as we see down here, in 1 kilocalorie. So kilocalories, kilojoules, joules, and regular calories, kind of, I guess, four common units, even though they're kind of based off the same ones, that for energy. Now, a lot of times when we talk about energy, we talk about energy as either sort of being released in a process or sort of being absorbed in the process. So we touched upon these earlier as well, but just to make sure, exothermic, when we talk about something being an exothermic process, that is when heat and energy is released. While when we talk about heat and energy being absorbed, that's an endothermic process. That's when heat and energy is absorbed. So when we talk about heat and energy, there's actually sort of a symbol or a letter that kind of represents it. And Q is sort of that letter, and that represents heat or energy. So a lot of times when we do a calculation involving heat or energy, we sometimes solve for Q. And we could relate exothermic or endothermic and the actual number value that you get for Q by really, not really the number, but it's actually the sign. So if you calculate Q, for example, and you end up with a negative number, that means that that reaction or process was exothermic and heat and energy was released. While if you calculate Q and you end up with a positive number, that means that heat and energy was basically absorbed by the system or whatever it may be, absorbing that heat and energy. When we talk about sort of heat and energy being given off and heat and energy being absorbed, that relates also to that law of conservation of energy. And basically, what that states is we basically don't create nor destroy energy. It is sort of transformed from one form to the next. But ultimately, a lot of times when we think about this idea, we think about the idea of, if something loses a certain amount of energy, there will be something that gains the exact same amount of energy. And usually, when we're talking about that situation, we oftentimes talk about the system and really the surroundings. So the system is really anything you're interested in the context of sort of chemistry. Could be like the test tube you're doing the experiment in, the beaker you're doing the experiment in, the flask you're doing the experiment in. The surroundings is pretty much everything outside of that. And what that means is, for example, is if the system loses heat and energy, for the system, Q would be negative, is giving off that heat and energy. And what that would also mean is somebody has to absorb that. And for our surroundings, that means Q would actually be positive. It's going to absorb all that heat and energy being given off by the system. Now, the surroundings can actually release some heat and energy. and it would be Q for the surroundings being negative. Where's that energy from the surroundings going to end up? Well, it's going to end up right back in the system here. So the system would then be positive for the Q or the heat and energy in that particular case. The conservation of energy tells us that basically, if we just take our system, for example, here, and we just make up a number and say, hey, this system just gave away 50 joules of energy. It released 50 joules of energy. If it released 50 joules of energy, what that would mean is it would actually be negative 50 joules of energy because the system is releasing it. What would that mean for our surroundings? Well, for our surroundings, it would actually absorb the exact same amount of energy, 50 joules. The difference, though, it would actually be a positive value for it because that indicates that the surroundings is absorbing that energy, and the negative for the system means that it is giving off that energy. The actual value or amount of energy being transferred from, say, the system to the surroundings in this case is the exact same amount of energy. The only difference is one is giving it away and the other one is going, thank you very much, and kind of picking it up. So, that's essentially when we think about energy and how energy flows from one place to the next. That's sort of what we think about in terms of happening. And that's why it's oftentimes when we're calculating things like energy, it's important to, make sure that you keep the sign that you get. Is it positive or is it negative? Because in the context of energy, it's a very big thing, the negative or positive. It allows you to understand if it is negative, that system, for example, or whatever it may be, is actually giving off that heat and energy. While if you calculate it as positive, what that's going to tell you is the heat and energy is going to be basically absorbed, by whatever it is, the system, you. So, for example, if you had sort of like a Bunsen burner that was burning, that Bunsen burner is obviously giving off a lot of heat and energy through the flame, right? So if you carefully put your hand near it, again, not in the flame or ever on the fire, but if you put your hand near the fire or the flame, you will feel all that heat and energy coming off. And the relationship that's sort of happening there is the Bunsen burner is giving off all that heat and energy. So it would be negative or exothermic. And if your hand is near there, your hand is picking up that heat and energy coming off from that Bunsen burner, and it would be endothermic for you and positive, and probably would hurt, which is why we don't put our hand near fire, right? So, but the idea there of the exchange of energy is sort of constant in that sense that whatever is being given off, there's somebody that is essentially absorbing the exact same amount of energy. Now, when we talk about specific heats, there's usually an equation that we could use to calculate specific heat. And the specific heat equation, and again, you're not going to be responsible for actual calculations using this equation, but as I mentioned earlier, I think it may help for the better understanding of the rest of the topics we're talking about here. But the specific heat equation is Q is equal to ms delta T. And when would we use this equation? Well, this equation is used when a substance is in the same state. So it's either solid, liquid, or gas, but the temperature of that substance is changing. So what does that mean? Well, for example, you could use this equation to figure out how much heat water would absorb if you put some hot pieces of metal in it. Even if you drop some hot pieces of metal into water, water is going to most likely stay still liquid at that point. If you just took a piece of metal by itself and you heated it up, the metal probably is not going to change its state, it's going to remain solid. But in both cases, the water or the metal, the temperature of those guys will change depending on what you do to them. So that's what we use the specific heat equation for. What does all these sort of values sort of mean in this equation? Well, Q is heat or energy, and it will have units of joules or calories usually, again, depending on which one you choose. M is mass of the substance, and the mass of the substance is in grams. Delta T is the change in temperature. And that's defined as the final temperature minus the initial temperature. And I know we just talked about temperature here in this chapter, and oddly, in this equation, it's actually one of the few in chemistry that most of the time we keep it in degrees Celsius and not convert it to Kelvin. And that's really because most of the time in chemistry, when we grab a specific heat capacity, which is what S stands for, it is usually in units of joules per gram per degree Celsius or calories per gram per degree Celsius. So because of these degrees Celsius, again, it's one of those rare times that we actually do keep our change in temperature in degrees Celsius. For reference point, substances do have different specific heat capacities depending on what it is and also what state it is, but liquid water is a common one that people sort of reference. Liquid water has a specific heat capacity of 4.184 joules per gram per degree Celsius, or if you're doing calories, 1 calorie per gram per degree Celsius. So those are two values that are commonly used for liquid water. By the way, like I said before, it does change with state. If you want a specific heat capacity of ice, which is solid water, it's like 2. If you want the specific heat capacity of steam, which is basically the gas version of water, it's also about 2-ish and some change. So things do change depending on the state. Usually there's a table where you can look up these values, and you would want to look it up obviously for the substance and the particular state it's in. But really, what does specific heat capacity really mean? Well, the definition of it is how much energy, which is like joules, needed to raise 1 gram of a substance by 1 degree Celsius. But basically, what it means is the larger the value for the specific heat capacity, usually it means it takes more energy just to raise that substance 1 degree Celsius. So, for example, if we took something like liquid water here, it has a specific heat capacity of 4.184 joules per gram per degree Celsius. What that means is to raise liquid water by 1 degree Celsius, you got to put in there about 4.184 joules of energy for every gram of water. Compare that to perhaps like a metal that's like, say, 0.45 joules per gram per degree Celsius. This is a significantly smaller number for this made up metal. And that basically means you only need to put in there 0.45 joules for every gram of that metal to raise it by 1 degree Celsius, which means if you sort of put the same amount of energy into both of them, you would probably expect the metal to heat up more than water would in that case, right? Because you don't have enough energy to kind of make that big difference. Also why, people get very concerned when the, waters of the world there goes up by like, a degree Celsius or something like that. That's a very large specific heat capacity. So in order to make even that 1 degree difference in the temperature, it takes a lot of energy to do that. And that's why, sometimes there's a lot of concern, obviously, about rising temperature water levels and stuff like that. So, when we look at specific heat capacity, we could use it to gauge how much energy is needed, again, really to sort of change the temperature of a substance up or down. But again, we're still keeping that thing in the same state. So, for example, if we just did a quick calculation just to kind of show you if you did a calculation, you want to know how much heat is required to raise, we'll just make it up, 125 grams of a metal with a specific heat capacity of, I'll use the one I think I just made up, 0.45 joules per gram per degree Celsius from 52 degrees Celsius to, we'll go with 99 degrees Celsius. So if we were going to do this, we would use our specific heat equation. Again, the metal, if we heat it up, is not going to change. It's going to be solid. We have the mass given to us, which is 125 grams. We have the specific heat capacity given to us. The initial temperature is 52 degrees Celsius. Final temperature is 99 degrees Celsius. So if we wanted to figure out the heat, we would plug it in and we would have 125 grams. We would take our 0.45 joules per gram per degree Celsius. And again, we always want to do final temperature minus initial temperature. And if we do that, and we grab a calculator here, take 125 times 0.45. We're going to times it by a 99 minus 52. Going to end up with 2643.75. In terms of units, grams would cancel. Degrees Celsius would cancel. We would be left with joules. Significant figure wise, you may be wondering, what should our significant figures be? Well, we're really multiplying here, but we are subtracting right there. And if we subtract right there, that's 47 degrees Celsius when you subtract it. That is 2 sig figs. This guy is 2 sig figs. And this guy is 3 sig figs, which means technically this guy should be 2 sig figs on the answer. Should be something like 2,600 joules of energy. Now, the answer we got here was a positive number, which would tell us this is a endothermic process. And that makes sense, right? Because we started at 52 degrees Celsius, we heated it up, we ended up at 99 degrees Celsius. That piece of metal gained energy in that process, right? So what would it be perhaps if we had the opposite sort of thing happen and we ended up with a exothermic process? Well, we could even take the same piece of metal if you want, and we put it in the freezer. And we started with the 125 grams of that metal. Again, it still had the same specific heat capacity. But in this case, we started at 52 degrees and maybe we put it in the freezer, and let's just say it went down to, we'll do 2 degrees Celsius. How about that? So we did 2 degrees Celsius at that point. How much heat is required in that case and what happens with that? So if we use our Q, we would do our MS delta T. Remember, 52 is where we're starting with our initial temperature. 2 is where we're ending. So we put our numbers in, and again, the 125 would be the same. The 0.45 would be the same. So it really is this change in temperature that's going to affect whether or not it's endothermic or exothermic. In this case, we actually stopped at 2 degrees Celsius when we kind of froze the metal, minus our initial, which was 52 degrees Celsius. And if we do that, we will end up with minus 2812.5. Again, joules is what's going to be left over as our Celsius cancels, our grams cancel. Sig fig wise, again, when you subtract that, you got about a minus 50 degrees, which is where the negative comes from. And that's 2 sig figs. This is 2 sig figs, and this is 3 sig figs, which means we should end up here. at minus 2800 joules. Again, the negative here is important because that means that this is a exothermic process. So what you see here with the specific heat equation is, again, even if you put that piece of metal into the freezer, it's still obviously going to remain solid. And the part of it that actually affects whether or not, it's going to be an endothermic process, which absorbs heat and energy, or an exothermic process is really that change in temperature. So if you increase the temperature on a substance, that means the only way to really do that is for the substance to gain energy. And if you decrease the temperature on a substance, the only really way for a substance to do that is to release energy, which would be exothermic. Okay, so again, I just did two calculations, and again, I'm going to stand by what I said earlier, that you are not responsible for a specific heat or those calculations, but again, hopefully it'll help you sort of understand what that is, and again, understand a little bit more about as we continue on here. So let's continue on and talk about changes of state. And as we mentioned here, it is when we sort of transition from one substance to the next, or one state to the next. I don't want to say one substance to the next, but actually one state to the next. And the first one we're going to talk about is that melting and freezing process. And as we can see in the picture here, that is the process when it goes from solid to liquid, or liquid to solid, as we see down here. And we see the same thing here, going from solid to liquid. That is endothermic, which is why it says plus heat in that case. Going from liquid back to solid, that is negative heat, which is exothermic. So again, heat and energy has to be released in that process. When a substance starts to melt from solid to liquid, that is what is referred to as the melting point. And when it goes from liquid to solid, that is what is referred to as the freezing point. As I might have mentioned that before, and sometimes confuses people, is this actually does occur at the same temperature. So for example, if we're talking about water, that is 0 degrees Celsius, 0 degrees Celsius, put the 0 in there. 0 degrees Celsius is where that transition occurs. And exactly right on that nose, when you're at exactly, that's a bad straight line, but I did my best there. When you're exactly the temperature of 0 degrees Celsius, that is when that transition occurs, going from solid to liquid. You are not actually, when you're doing that transition, you are actually not changing the temperature. You're going to take the substance from solid at 0 degrees Celsius right over to liquid at 0 degrees Celsius. So you have that transition occurs exactly at 0 degrees Celsius. At 0 degrees Celsius, you got kind of both states happening at once, kind of like ice crystals. If you want to think about water, got some solid, you got some liquid. Not until you get a little bit above 0 degrees Celsius that you get liquid water, not until you get a little bit below 0 degrees Celsius that you get solid. So right there in that sort of as a plateau, we'll see a graph right here in a second. That's exactly when that occurs. So what determines sort of which way you go? What determines which way you go is actually what I circled down here. If you're at 0 degrees Celsius and you continue to put heat and energy in, you will go from solid to liquid, the process of melting. If you're at 0 degrees Celsius and you continue to take heat out, like throw it in the freezer to remove heat from that system, you will then go the opposite way towards freezing. Now, since we're talking about sort of the heat related to this, there is again a certain amount of heat that's required just to do that transition. Again, not change the temperature, but to take a substance from solid to liquid at the exact same temperature, or backwards from liquid back to solid at exactly 0 degrees Celsius. And that is what's known as the heat of fusion, sometimes abbreviated delta H of fusion. And this is what is sometimes referred to as the heat of fusion. And delta H is outside of our class, but delta H is what is actually referred to as the enthalpy. And enthalpy is a fancy letter and symbol for basically the heat of a reaction. So that's basically what it means. But the delta H of fusion, or the heat of fusion, is the energy that's required to change 1 gram of a substance. I'm not sorry, to change basically the substance from solid to liquid, or liquid back to solid. For water, that heat of fusion is about 80 calories per gram to do that, or about 334 joules per gram to do that. So for every gram of water that you want to change into liquid water from solid requires 80 calories per gram, or 334 joules. Now, the sign is also important. So we've been talking about the idea of the sign and endothermic and exothermic. So if we were going to take water in the solid state to water in the liquid state at 0 degrees Celsius, that would require a positive 334 joules per gram to do that. Again, endothermic, got to put the heat and energy in. If we started with liquid water and we wanted to end up with ice or solid water, again, at 0 degrees Celsius, we're not changing the temperature. That would require the same amount of energy, but it would be negative 334 joules per gram. Negative because that's an exothermic process, positive for the other one because that is a endothermic process. So again, the same amount of energy as we were talking about earlier, that sort of conservation of energy, but the sign is different depending on which way you go. So kind of like we just saw with our specific heat calculation, we got a negative sign when we were releasing that energy, and we got a positive sign when something was absorbing that energy. Same thing here as we do that transition from one to the next there. And again, we could use these as conversion factors here by basically figuring out how much heat just to simply change that substance from solid to liquid, or liquid to solid, is just simply you take the mass times the heat of fusion. This number that we're looking at here, the 80 calories per gram, or the 334 joules per gram, is specific for water. But other substances have other values for heat of fusion, and it does vary depending on your substance. But a lot of times we deal with water, so a lot of times you do see water sort of given often. But again, if we weren't dealing with water, a couple of things would be different. First off, it wouldn't be this specific value for the heat of fusion, and it wouldn't have necessarily 0 degrees Celsius as its freezing point or melting point. So if you change the substance, the heat of fusion will change, and also obviously where it melts and where it freezes will change. So if we were to do this sort of calculation here, how many kilojoules are needed to melt 32 grams of ice at 0 degrees Celsius? So what we're talking about is we're sitting right at 0 degrees Celsius, and we have ice, and we want to take it to liquid water. Again, not changing the temperature, just simply going through that transition. And again, that is definitely where we would use our heat of fusion. And since it wants kilojoules, I'm going to use that relationship in joules. 334 joules per gram is our heat of fusion for liquid water. And I'm going from ice to liquid water, right? So that means it's going to be an endothermic process, which means I want a positive value there. So to set this up, we would start with our 32 grams of ice, which is basically water. And we would use our heat of fusion as a conversion factor. Again, positive number here because we are going from solid to liquid. The grams will cancel, and we will end up with their 32 times 334. That's going to give us 10688 joules, but we want kilojoules here. So remember, there are 1,000 joules in a kilojoule. We would use that as our conversion factor. 1,000 joules on the bottom, 1 kilojoule on top. We're essentially dividing by 1,000 at this point. Going to give us 10.6, what we got there, 10.688 kilojoules at that point. Now, significant figure-wise, well, that's about 3 sig figs. This guy's also 3 sig figs, which means probably should end up with 3 sig figs here. That's going to be 10.7 kilojoules needed to simply take that piece of ice. It needs to pick up that energy, endothermic, which is why it's positive, in order for it to end up as nicely drawn red water liquid there at 0 degrees Celsius. So this is how we can do this calculation, which again, you are sort of responsible to know how to do this particular type of calculation here, of using the heat of fusion to figure out how much energy is required basically to melt that piece of ice. So let me ask you sort of an important question is, well, what happens if I started with the liquid water and I wanted to get my ice back? What would really be different in this calculation? So let's just say, for the sake of argument, we actually want to go the opposite way. We'll go back that way. Well, if it's all the same, we would technically set it up exactly the same. We would still have our 32 grams of water. We would still use our heat of fusion, which is 334 joules per gram. We would still get the 1068 joules. We would still do our conversion of 1 kilojoule per 1,000 joules. We would still get our 10.688 kilojoules, which we would then round to 10.7 kilojoules. So you may be saying to yourself, well, if it's the same calculation, should it be? And the answer is, it's really not, because if we're going from liquid to ice, that is a exothermic process, which means we're talking negative here. That means that we would technically use the same number, but it should be negative 334 joules per gram, which means we should have a negative here because it's exothermic, which would obviously give us a negative here, would give us a negative there, and we would end up with a negative there, which would be exothermic. So you can see it really is the same calculation. The difference here is that positive or negative to indicate that it is endothermic or exothermic. Technically speaking, you could do it all the same, and at the end put the positive or negative sign in, if you understand, sort of the process that's occurring. Is it endothermic or exothermic? All right, so that is our melting and freezing. The next thing we're going to talk about is sublimation and deposition. Sublimation is that process where we go directly from solid to gas. So we skip the liquid state altogether. Deposition is the opposite, where we go from gas directly to solid, also skipping the liquid state. This also requires, as you go from solid to gas, energy to be put in, which means it's endothermic in that process. Going from gas back to solid, energy needs to be released, which is why we have our negative there, which is exothermic in that. When we release the energy, these gas molecules flying around slow down and they basically clump together into the solid state. Dry ice is an example of that, going from solid directly to gas, no liquid cleanup. By the way, dry ice is actually not water. In case you don't know, it is CO2, carbon dioxide. Very, very cold. Don't touch it with your bare hands. But if you ever seen dry ice or used dry ice, it basically goes from solid directly to gas. Again, none of that liquid cleanup. Deposition coming the other way, going from gas directly to solid, no liquid part. That's the process they used to use. I guess they still use it for like CDs, DVDs. They're kind of shiny on top. That was the process they used to use for that. If you're not sure what that is before streaming, go Google it. But if you look at like a CD or DVD, usually kind of very shiny up on top. And that's sort of the process they use to kind of deposit certain metals on top of those guys. The other sort of important transition is evaporation or vaporization and condensation. So this is the process where we're going from liquid to gas. So here we're going from liquid to gas, our gas back to liquid. Again, our liquid to gas is evaporation or vaporization. Gas back to liquid is condensation. This also occurs at the same temperature. So for example, for water, that's 100 degrees Celsius where that occurs. And the same thing with like we were talking about with freezing and melting, dead on there at 100 degrees Celsius, you have gas, you have liquid water, and you have basically both phases happening exactly at the same temperature. And that transition occurs at the same temperature. So when you're transitioning, say, water at 100 degrees Celsius, it remains at 100 degrees Celsius as it goes from liquid to gas at 100 degrees Celsius. Same idea, not until you get a little bit above 100 degrees Celsius, you really do get gas. Not until you get a little bit below sort of 100 degrees Celsius, do you get liquid water. This occurs at the boiling point of a substance like water's boiling point is 100 degrees Celsius in this particular case. So at the boiling point, that's when really molecules gain sufficient amount of energy to really overcome all the forces that hold them together and allows them to escape. So as you boil, you usually will see these big bubbles start to form. And what that has inside those bubbles are kind of like water molecules or water vapor. And when it has enough pressure to keep the bubble, it goes to the top. Once it gets to the top, obviously it pops and allows the water to escape as that steam that you see coming out of the beaker as it's boiling. You may also know that or notice if you ever like made some water there to cook some pasta or something. And like as soon as you hit it with the fire, great drawing of a fire, I suppose. As soon as you hit it, you might notice like a lot of not really bubbles, but people sometimes think they're bubbles. A lot of like little kind of bubbles kind of forming there right away, and then they really don't go away. That's basically what's happening there is as you hit it with that heat really quickly, it's making a lot of like CO2, for example, insoluble in the water. So that's what you're seeing is those like quick gases kind of coming out really quick, like CO2 that, becomes a little bit less soluble in water as soon as you hit it. Then it kind of goes away. And it's not really again until you really get those some substantial looking bubbles that are happening there that you really do get sort of that water to boil. And that's because you even know sometimes you'll get some bubbles that will form, but they'll never kind of make it to the top. And that's because the pressure inside is less than the pressure outside. And kind of those bubbles burst before they make it to the surface. But really, at some point, the pressure will equalize inside and outside of those bubbles, and it will allow them to successfully sort of navigate themselves to the surface there. And it's at that point you really do have the boil. Sometimes in the lab, when people heat up water, they they see that first effect that sort of occurs really quickly and go, oh, cool, my water is boiling. And then it's really not boiling because it's like cold as it started at, basically. Again, it's not till you kind of get that raging boil there that you really do have, your water kind of really boiling. By the way, when we talk about boiling, sometimes we see a thermometer in here. Sometimes people get nervous on the thermometer because a lot of thermometers in the chemistry laboratory, they max out about 100-ish, not too much higher than that. So people are always concerned that, am I going to break my thermometer, when I start to boil? And the answer is no, because that boiling point is right there at 100 degrees Celsius. That's basically where the water will boil. It really won't continue to get very much higher after that in most cases. And you don't have to worry about, your thermometer sort of breaking and stuff like that. So it's usually able to sort of maintain that 100 degrees Celsius, because a little bit outside of our class, but odd as it may sound, even though you're heating it, when something boils, it's actually a cooling process, which is outside of what we'll talk about here. But the quick answer is, or the quick sort of answer to that sort of situation is, even though you're heating from the bottom, you're kind of cooling from the top. So when your thing starts to boil, that's why it's able to kind of maintain, in a perfect world here, 100 degrees Celsius. There's a lot of other things that affect, obviously, the boiling point, things like pressure and stuff like that. If you go boil water in a city at a higher elevation, it may boil at a different temperature than 100 degrees Celsius because of the pressure. But as odd as it may sound, that process of boiling is kind of overall like a cooling process. And that's why, even though you think about, I'm continuously adding heat, how come like my temperature stops there at 100 and doesn't keep going? It's because of that. So as quick as you kind of heat it from the bottom, kind of cools from the top, it kind of allows it to maintain that 100 degrees without, again, popping your thermometer and stuff like that. So here's our picture. And again, same idea as we've been talking about with the other transitions that occur at the same temperature here. Endothermic here for our liquid to gas. We got to put that energy in to do that. Exothermic here as we go from gas back to liquid. Our negative there, we got to release that. And again, that's going to allow, like we've talked about, kind of these guys not to have enough energy really to fly past each other, kind of going to start sticking to each other and drop into the liquid. By the way, at the surface of any liquid, you basically have that happening. You got some guys going out of the liquid into the gas phase. You got some guys going from the gas phase back into the liquid. That's why, for example, when we have like a spill of some liquid on a counter and it's kind of spread out, at the surface of that liquid, you have a lot of evaporation occurring, but you also have some condensation occurring, some of those guys coming back in. The difference, though, if you have sort of a liquid that's on, say, the counter and you spill a couple of drops, as you get that rate of evaporation, you have air that's there. It's going to push all that water molecules away, which means they're not available to come back in to that liquid phase. And eventually what you'll see, right, is your little spill will get smaller and smaller. Again, as those air molecules push away the water that has been lost through evaporation, it'll eventually evaporate away. Also, why, if you, instead of having like a little spill that's all spread out on the countertop, but you fill a big beaker or glass with water, you will get some evaporation, but you have a longer way for that to go because there's only so many water molecules that could get to the surface. It gets pushed away. So it takes much, much longer, obviously, for that sort of beaker of solution to evaporate than if you had just a little spill on the countertop. So is there energy associated with going from liquid to gas or gas to liquid? There is, and it's the heat of vaporization, also sometimes abbreviated delta H of vaporization. And it works the same way. This, again, is that energy required to go from, if we were, say, water in the liquid state to water in the gas state, or water in the gas state to water in the liquid state. So, for example, for water, it is 540 calories per gram, or 2260 joules per gram. So again, this number is specific for water, and water has a heat of fusion of 540 calories per gram, or 2,260 joules per gram. Works the same way. If we're going from liquid to gas, that's endothermic, that would be plus 2260 joules per gram to do that. If we're going from gas back to liquid, that would be exothermic. That's going to be minus 2260 joules per gram to do that. One note while we're talking about that number, if you compare the delta H of fusion for water, if you remember, it was 334 joules per gram versus the delta H of vaporization for water, which is 2260 joules per gram. It takes a tremendous amount more energy to do this transition going from liquid to gas than it does to go from solid to liquid, which is our heat of fusion. Why would that be? Well, going from solid to liquid, in the solid state, everybody's packed pretty close. In the liquid state, everybody's still relatively packed pretty close to each other. So it doesn't take as much energy to do that transition. But as we go from liquid to gas, in the liquid state, everybody kind of packed near each other. In the gas state, everybody's completely broken apart from each other. It takes a lot more energy to break everybody apart. And we can see that with the actual number here, about 2,260 joules to do that transition, completely taking everybody apart from each other, or breaking everybody apart, while it only takes 334 joules to sort of break everybody apart, I guess is a way you could kind of word that. So that's the heat of vaporization. And again, it could be positive or negative depending which way you go. Heat of condensation, again, it's the same number, but it would be negative based on what we're talking about. Most of the time, people call it the heat of vaporization rather than the heat of condensation. So this is really the same as the heat of vaporization. And again, you probably should use it as negative going in that direction. So there's our conversions that we could use. And again, if we were going to calculate that like we talked about previously, we could use those as a conversion factor. So let's take a look at one. How many kilojoules are released when 50 grams of steam condenses at 100 degrees Celsius? So we're talking about steam, which is the gas phase going through condensation, which means we're going to end up in the liquid stage. That is a exothermic process, which means we are going to use our delta H of vaporization for water. Steam is water. And because of that exothermic, that would be 2260 joules per gram negative. So we would take our 50 grams of steam, our water, if you want. We will use that as a conversion factor, minus 2260 joules per gram. Grams will cancel. We will end up with 50 times minus 2260, going to be minus 113,000. These will be joules. Again, we're looking for kilojoules. So 1,000 joules equals a kilojoule. 1,000 joules is a kilojoule. Joules will cancel. And that would get us minus 113 kilojoules. Now, in terms of sig figs, you got like about 3 there. Got about 3 there. And we ended up with 3 there. So that's good. Again, negative as we would expect it to be because we're going from gas to liquid. It has to remove that energy to do that. And just like the previous calculation we talked about, if we were going the opposite direction, if we were in this case looking at it going from looking at it going from liquid to gas at 100 degrees Celsius, everything would be the same, except again, this would be a positive number, which would yield us positive 113 kilojoules of energy. Again, if you follow through the whole calculation, just turning that guy into a positive that I circled, because that would be, again, a endothermic process if you did sort of the opposite one. This also, again, demonstrates that idea of sort of that conservation of energy. Again, it takes a certain same amount of energy either being given off or absorbed, to make certain transitions. So again, you are responsible for heat of fusion, what it is, and obviously those calculations, and also heat of vaporization, what it is and those calculations. So let's talk a little bit about kind of putting everything we talked about together, which is a heating curve, sometimes referred to as a cooling curve. A heating curve is where we go from, in this case, solid to gas. We're adding heat as we go through it. So if this was water, like in the picture here, we could see our ice basically we're starting with. We have our liquid water, and then obviously we have our steam that's up here. If we go right along, we can see these areas where it's plateaued at 0 degrees Celsius. That is where we're doing that transition of going from solid to liquid, liquid to solid. And again, the amount of energy required to do that is where we use that heat of fusion calculation to do that. If we go over here at 100 degrees Celsius, that is a flat plateaued line, which means the temperature is not changing because it's flat. So if we look on the temperature scale on the left, it's just flat across. Temperature remains 100 degrees all the way across there. And that is where we go from liquid to gas or gas back to liquid. And that is where we use our delta H of vaporization to do that transition. Now, when we look at this heating and cooling curve, and I'll just kind of re-sketch it real quick, we see a couple of things. And again, if I come this way, this is 0 degrees Celsius. This is 100 degrees Celsius. This is ice down here. That is liquid water. And that is steam up here. Again, as I mentioned before, is not until you get a little bit above kind of the boiling point or the melting point that you do get ice or liquid. So for example, here, if we're right here at 0 degrees, it's not until we get below 0 degrees really that we really truly have ice. If we're right here at 0 degrees, it's not until we get a little bit above 0 degrees that we actually have liquid water. Same thing when we get to 100 degrees. When we get to 100 degrees, which is right here, again, not until we get below that 100 degrees, we have liquid water. Not until we get above that 100 degrees that we have steam. Right at 100 degrees, again, as we talked about, we have kind of both things together. We have liquid and gas happening. Right at 0 degrees Celsius, we also have solid and liquid happening at the same time. Now, if you were going to do a calculation where you want to know, hey, how much energy is required to take ice all the way up to steam? When we look at a heating or cooling curve, there's a couple things that we use for our calculation to do that. And let's take a look at a cooling curve real quick. Cooling curve is really just the opposite happening. We're actually removing heat and energy. So we're starting with the steam that's way high and coming down to our ice. And again, we're removing energy exothermic in that process, but we see the same things. We see our 100 degrees Celsius line here, and we see our 0 degrees Celsius line. We also see the difference in the size of it. As we talked about, it takes a lot more energy to do that transition going from liquid to gas or gas to liquid than it does going from solid to liquid or liquid to solid. Now, if you were sort of to do that calculation that I just sort of talked about, where we have, again, I'll redraw the curve here a little bit. This is, again, steam up here. This is liquid water. And this is ice. And again, if we come across here, that's 0 degrees Celsius. Come across here. Ideally, these would be straight lines, 100 degrees Celsius. Now, when we look at this, there's a couple of things that are happening in terms of energy and heat. The first thing, for example, that's happening is if we started to say here, is maybe minus 5 degrees Celsius or something. If I want to take the ice all the way up to steam, the first thing I would have to do is heat up that ice from minus 5 degrees Celsius to 0 degrees Celsius. So the first thing I would have to do is take my ice at minus 5 degrees Celsius to ice at 0 degrees Celsius. Now, how would I calculate that? Well, ice at minus 5 degrees and ice at 0 degrees Celsius is still the solid state. And this is why we talked at the beginning about specific heat. I am keeping the substance in the same state, but I am changing the temperature. That would be my Q is equal to ms delta T if I want to know how much energy is required to do that. So I would put my values in. I would want to make sure I use the specific heat capacity for ice because it's ice at this point, not liquid water. The change in temperature would be final temperature 0 minus initial temperature, which would be minus 5, and whatever the mass is. So that would be the first step that I would need to do to take it from ice all the way to steam. The next thing that actually would need to occur in this case is you would be now sitting here at 0 degrees Celsius with ice. You would need to take it from 0 degrees Celsius ice to 0 degrees Celsius liquid water. This is a phase change that we just talked about. We would then have to go from 0 degrees Celsius ice to 0 degrees Celsius liquid water. Here we changed the state, but we did not change the temperature. So what we're doing here is basically the heat of fusion. So we would do a heat of fusion calculation for the second part here. After we would do that, we would be sitting at 0 degrees liquid water. The next thing that we would do is go from 0 degrees liquid water all the way up to 100 degrees liquid water. So we would go from, I'll go step 3 up here, 0 degrees liquid water to 100 degrees liquid water. So again here, this is all the same state. This is all the same state, which is liquid, but we are changing the temperature. So at this point, what we would calculate is using the specific heat equation. And again, in this case, the change in temperature would be 100 degrees final temperature minus 0 degrees initial. Specific heat capacity in this case would be the one for liquid water, which would be 4.184. And obviously whatever the mass is. So we want to get to steam. We're still actually, believe it or not there yet. The next thing that would occur would be we need to go from 100 degrees Celsius liquid water to 100 degrees Celsius steam. So 100, number 4 here, would be taking it from 100 degrees liquid water to 100 degrees gas, basically, our steam. And that is the same temperature, but different state. So that transition is really going from liquid to gas. We would use our delta H of vaporization calculation here. And I didn't really originally say where we're going to stop, but let's just say we took it to 102 degrees in terms of the final temperature. So if we took it up here to 102 degrees, the last step would be right here at that point. And that would be taking it from 100 degrees steam to 105 degrees steam. That is the same phase, but different temperature. So to calculate that, we would use our specific heat capacity. So again, this is why I kind of talked about specific heat capacity earlier on. You're not required for the calculation, but this is how we would look at a heating or cooling curve and figure out, the energy associated with it. So how would we figure out the total amount of energy? Well, the total amount of energy is very much easily found by simply adding all those steps together. So the total energy would be step number 1 plus step number 2 in our case, plus step number 3, plus step number 4, plus step number 5. Basically adding all of the energy values you get together, and that will give you the total amount of energy to go all the way through that. So again, we're not going to do a calculation like this in this class, but I did want you to sort of understand sort of when you read it, for example, sort of what's going on with it. Again, in terms of calculations involving these energies, the heat of fusion you're still responsible for, just a basic heat of fusion calculation or a basic heat of vaporization calculation. So we do have some questions here about a plateau line on a heating curve represents a constant temperature and also a change of state. So if you look at those heating curves, wherever there's these plateau lines, straight lines, that's a very badly drawn straight line, a straight line, basically what that means is because temperatures on the Y, we are not raising the temperature, we're keeping the temperature constant, and that only occurs when we change states, either solid to liquid, liquid to gas, like we talked about, those changes of shape. A slope line, which are those lines that were in between those coming upwards, that is when we keep this state constant, but we do change the temperature. So again, this is where we would use either the delta H of fusion in the calculation or the delta H of vaporization, depending on what calculation you're doing. This would be where we would use Q is equal to MS delta T if you were doing that calculation. Now we got there, it's good. And lastly here, using the cooling curve, answer the following for water. Water goes through condensation. That occurs at 100 degrees Celsius. Again, condensation going from gas back to liquid occurs exactly at 100 degrees Celsius. At temperature of 0 degrees Celsius, liquid water will freeze. That's the freezing point of it. And it wouldn't melt because we're talking about at this point liquid water at 0 degrees Celsius. Because it's already liquid, if it melts, it's not going to melt because it's already liquid. So its only option is to go towards the solid side. At 40 degrees Celsius, liquid water would be, well, this is 0 degrees Celsius. At 100 degrees Celsius, that's where we get our gas to occur. So 40 would be in between. So that is still liquid at that point. So that would be liquid. And when water freezes, heat is removed. So again, basically, as we go from gas to liquid to solid, we're removing that energy. And just that process is, as we remove energy, they slow down, they kind of clump. Remove more energy, they clump even more, and everybody gets into the solid state. All right, so I think that now wraps up chapter 3 here. And again, like I said, in terms of responsibility, you will not have to do a specific heat calculation. Again, I hope it helps you better understand what we were talking about when we're talking about changes of state. Again, in terms of calculations, the heat of fusion and the heat of vaporization, like those couple we did here in this lecture, you are responsible for, and obviously knowing what happens as we go from solid liquid to gas and gas liquid to solid in terms of energy, and what the names of the transitions are: melting, freezing, evaporation, condensation, sublimation, and deposition, and obviously what those actually mean as well. All right, well, thank you very much for listening. And that will conclude the recorded Chapter 3 lecture.